University of Oklahoma Lookout, and he's here to speak to us today, and I'll let you take that one.
Alright, so my research deals with a particular signal phenomenon that occurs in the brain when a user is exposed to an inconsistent stimulus. Now, the title up there says P300 signal analysis and signal phenomenon exploitation for classification purposes. I apologize ahead of time, that sounds terrifying. It's actually going to get a lot better from here, I promise. So, my professor that I was working underneath actually was in Tokyo, and then I took this research and brought it back here to the States, you know, after the earthquake thing, just whatever. So, let's begin. So, brain-machine interfaces. Does anybody know what a brain-machine interface is, out of curiosity? Go for it.
It's your brain interfacing with the machine.
Thank you. Yes, yes. So, brain-machine interfaces. Since the dawn of man, we have had this as our way of handling tools and devices. As you can see from over here, we've got wrenches, we have hammers, we have screwdrivers, and before all of that, we even had sticks, pointy ones at that. Well, now that we're in the 21st century, I really hope that we can get away from using our hands and move more towards using our brains. Yes, as you can see there, as it gets bigger and smaller again. Now, how can we use our brain to interact with certain devices in the world? Well, first of all, we have to have a fundamental understanding of a lot of the activity that goes on in the brain. So, what we have to do is we have to measure the electrical activity. The electrical activity that we measure is called an electroencephalograph. As you can see here, actually, that is brain activity going on, and in the upper cortical regions of the brain that you can see here, that's higher cognitive. That's where you're doing your math. 2 plus 2 is 4, maybe 5, depends on your cognitive activity, I suppose. Now, over here, we would love to control this awesome new espresso machine. How would we do that with our brain? Well, we'd love to have all of that wonderful coffee, and we'd be able to tell the espresso machine, hey, make me coffee, and then it makes coffee instead of having to do the grinding and all of that business. Well, I assure you, there's no voodoo in this science at all. It's as simple as this, actually. You have that thing right there, and then you get this, and then you get there. You get an ANCAP. So, actually, what you have up here is the International 1020 system. It is the standard electrode placement on the scalp, not in the brain. We don't do that business anymore. Actually, we can measure signals from the scalp, so you can just wear a nice little hat, and it will measure all of the electrical signals going on in the brain at these standard 64 regions. So that would be an electrode, that would be an electrode, that one, etc. Now, here's where the fun comes in with my research. There's all kinds of wonderful signals in the brain. There are all kinds of event-related potentials, as they're called. The one that I particularly study is called the potential 300 signal, which is basically if you hear a bird chirp, and you hear a bird chirp, and you hear a bird chirp, then BAM! Suddenly, as you've all just experienced, you elicited a P300 signal response inside your brain, without even knowing it. What this is after I yelled the BAM, sorry about that ahead of time, well, actually post-time, you get a spike in voltage potential, which you can see here, and it occurs approximately 300 milliseconds after the stimulus. So, approximately 300 milliseconds after the stimulus, you get this giant spike. This blue one is the one exactly I'm looking for. This red one right here, that's just regular noise that occurs all the time. That's your 2 plus 2 is equal to 5 going on right there. And then afterwards, we send it to the computer, and the computer throws up its hands and says, what is this? And makes an output. Actually, this is where I live. I do the signal processing. I have to figure out, okay, how can we determine the red from the blue? Well, visually, it's pretty easy, right? Well, mathematically, it's a little bit hairy. And in fact, when I initially looked at the math, I was absolutely terrified about, threw up my hands and said, I'm never going to be a PhD candidate. Well, I found out 6 months later, it's not as complicated as I originally thought when I had a mild nightmare and thought to myself, hey, instead of using these crazy methods that most people use, I'm going to go ahead and stick with statistics. Statistics is a wonderful thing. It makes things so much easier. Now, well, at least for this particular situation, which I'll explain. Okay, so let's move on to the procedure. How do I detect this signal, and how does it exactly work? Well, not all parts of the brain are created equal. They all have different functions, as I'm sure you're all aware. Especially if you've had concussions, you're definitely aware. So up here in the upper cortical region of the brain, where you do the 2 plus 2 is 5, right? this is where, for most people, on average, you get the cleanest P300 signal. Because P300 signals are usually paralleled with higher cognitive functions. So when you're exposed to that, bam, that loud sound, or something just inconsistent, something that's different, it can be touch, it can be smell, it can be taste, it can be visual, which in my research it's visual, etc. And you can elicit this P300 response when you have that inconsistent stimulus. Back to the me yelling bam at you guys. Now, in other regions of the brain, it's actually not so clear. As you can see here, the P300 signal, which I've averaged over several times, is still really hard to see. It's this blue one. It's slightly different than the average noise, but it's not as clean as the upper cortical regions of the brain. Now, this is dependent on handedness, mental disabilities, age. It depends on a lot of things. The latency could be 450 milliseconds post-stimulus if you're 85. If you're 23 or you are 18, it's going to be a lot closer to 300 milliseconds, unless you've had concussions, for example. Then you get latency and you also get amplitude decay. Amplitude decay would be the signal would be much lower. Latency response would be the signal, the spike in voltage potential occurred over here instead. And that's dependent on many factors. If you're left-handed, congratulations, your P300 signal is a lot prettier. And it is also housed over here in the right hemisphere of the brain, as well as the left. Well, my research focuses on cross-correlation. So I take, this is where it gets scary, I take the permutation of all of the collected signals of P300 signals. So I take every signal of all 64 channels, I cross-correlate them, every permutation possible, and figure out which ones look mostly like an ideal P300 signal, which looks like this guy. If it comes out close to 1, it looks like a P300. If it comes close to 0, it's orthogonal, and it's probably not what we're looking for. And that's this little guy right here, for those of you that are familiar with calculus. If not, that's the magic that happens. So, how does this work? When we correlate our P300 signals with other P300 signals, we find we get a mound that's closer and closer to 1 as we average and get better channel selection. So, what happens when we correlate it with the noise, the 2 plus 2 is 5, instead of the BAM reaction? We find that it's a little bit closer and closer to orthogonal. So I thought to myself, in this mild nightmare that I had in Tokyo one day, that what if we could filter out the amplitude and the time at which it occurs for a human being? And again, this is where it gets difficult because every person is different, which is why we have averaging and the channel selection. So what I did is I selected, okay, we know it's going to be in the ballpark of somewhere a second after they're exposed to it. There's not really any outliers in the past, in research such as Donchen et al., etc., that goes anywhere beyond a second in latency. So it's safe to assume that if we have a peak detection around 300 milliseconds with our user, we can know that their P300 signal is probably housed right around there. It's personalized to each individual, the algorithm that I've made. Now, my filtering is when I put a range in which the peak can occur. If it occurs outside of this range, I reject the signal and I say it's irrelevant. It's nothing I'm concerned with. And when I did this, and I correlated it with the other signals as well as P300 signals, I got a stronger correlation, as you can see here, amongst other P300 signals. And we can see right here that regular EEG, the 2 plus 2 is 5, the irrelevant information, is increasingly orthogonal, which you can see from the last slide. That looked pretty gnarly. It's really hard to tell the difference between these two if you overlapped them. But now it's getting a little bit clearer. You can almost draw a line and figure out which one's the P300 signal and which one's not. So I took it a step further. I decided peak detection. If we average over a certain amount of time, noise over time approaches 0 when you average it, because noise is always all over the place. If you average it, it approaches some value. Ideally with EEG signals, it's around 0. Ideally. Now, with the P300 signal, though, the more and more you average it, the closer and closer it looks like this. So, what I did is I decided to filter out the amplitudes. The amplitudes being the height of the signal at that point. So, in effect, I drew a box. That's my research. I drew a box. And what I found was, look how orthogonal and how different noise is in the brain compared to when you correlate P300 signals together. It's nearly, I will not say it's 100%, it will never be 100%, but it gets so much closer to distinguish the signals from one another. It's so much easier. And the difference is, Most traditional methods use what is called support vector machines. It is a pattern recognition algorithm. It's complicated. It gave me a lot of nightmares, and that's when I threw up my hands and said I'm never going to be a PhD candidate ever in my life. It's impossible. But then, after I implemented the SVM, I did do it. It was horrible. I didn't like it, and it took 7, 8 months to do. This method took 6 days. And we can see that we get nearly 100% accuracy. And this is the best part. To use a support vector machine, you have to build basically this testing interface. It takes 20 to 30 minutes for a user. So can you imagine 20 to 30 minutes before you use a device that you want? That cappuccino, it's cold now, right? Well, with my method, it takes approximately 1 minute and 42 seconds. My implemented SVM method took 10 minutes and 42 seconds just to have it built, not tested. So, that being said, here are my references, and does anybody have any questions? Oh, by the way, this is a P300 signal in the back, designed by my fiance over here. Questions?
Is the P300 signal useful for the overall brain-machine interface, or is this just a part of cataloging overall brain responses to different stimuli?
Both. You can use it both. For my particular research while I was in Tokyo, we were building a wheelchair that could be automated. So what it ended up being is you see a matrix of places that you want to go on your wheelchair. It has a webcam interface. And the user can just look there, it'll flash a bunch of different places, and wherever the user's looking, it'll set off that P300 signal response, and that's how I know that's where they want to be. And so that's how it goes that way. Now, for cataloging purposes, it's important because over time, as the user uses it, you can average it and get a better idea, which is where support vector machines actually can be a little handy. But the problem is they can switch pretty often. But with the P300 response, you want it to be quick when you use a device. You want it to be fast, and so that's why I used a statistical method as opposed to the highly computational complex method. So, does that answer your question? Yes. Okay. Yes, sir.
Is it related to the P300? Is that a global response, like all across the surface of the brain, or is that, like you said, you found in the occipital lobe and the ventral, I'll call it ventral right now, but the ventral part of it.
Yeah. So
but is it global all across the whole entire brain, or does it just center around certain areas and you just know where to look?
ideally, it's in the upper cortical regions of the brain. That's a great question, and I hope I hadn't clarified it, but I'll elaborate some more. In the occipital regions of the brain, the response is actually really poor. It is a global response per se in the cortical regions, not the inner regions of the brain. But it gets a little messy. You can see actually a voltage dip right here, which is actually called the P300A, and the P300B is this spike right here. But the problem is when you correlate these signals together, it's not clear enough. It's clear to us visually that it's P300. I could tell you that that is P300 versus the regular signal noise that's going on in the brain, just because of that dip and that spike. And that's also because I spent like 16 months working on this work. I can tell the difference. But for math, for this correlation function to come out close to 1, it needs to look like this. So where you ideally find it in most people, let's say, I can't even give you an actual figure, but in most people, it's right here centered in the upper cortical regions of the brain. Most people are right-handed, so it actually tends to be a little bit closer to the language centers of the brain. But left-handed, it actually extends to both hemispheres of the brain, which is unique and wonderful to work with left-handies. So, but in that regard, yeah, it's a global response. It's just you get a clearer picture of what it's supposed to look like, or not necessarily what it's supposed to look like, but you get a better picture. It's easier to classify it when it looks like this much different.
I assume using software like NeuroGuide or any other kind of software that reads raw EEG data from out of the flesh and this kind of stuff.
Actually, yeah, we do online testing. So we have portable EEG devices that you wear on your scalp.
And also I'm talking
Oh.
about a computer program that would take raw data and convert it into your different frequencies of alpha, beta.
Actually, well, you can use software like that. I just took the raw data and I used the statistical method right on the raw data. So as the data was scrolling through, that's actually how I classified it. So people who have like ALS, for example, they're paralyzed from the neck down, we really are hoping that they will be able to have a better standard of living. They won't have to be as dependent on people, and we're really hoping that over time with methods like this, and there's so many phenomena out there that we use, and so many different methods that we use in this field of research, that it's becoming a global community to come together and build devices. For example, there's research in Germany where people are using a car, they're driving a car with this device called emotive epoch device. And they can drive the car through town, no problem. It'll stop at stoplights, etc. It's kind of like the Google car, but you also wear a wireless device as well. There's bicycles, there's wheelchairs, there's even food feeding devices out there that are being developed. So there's even this really fun toy where it can kind of read your emotions, and there's these bunny ears and it'll flop when you're sad, etc. There's all kinds of applications for this. One of my favorite ones is actually, I really hope in the future, it's time.
It is time, but just be aware that people may be walking in and out, so feel free to keep going until 3:20.
Okay, so yeah, one of my favorite ones is, and this is one I really hope happens in the future, is you can walk into your house wearing just a baseball cap with a couple of very thin electrodes or something. You could wear this baseball cap, or even some kind of net, or just anything, whatever is fashionable at the time, I suppose. And you can, instead of, with the Xbox Connect, Xbox, Netflix, whatever, right? You can just sit there and say, you don't even have to say anything, actually. You just look at the TV, and the TV pops on. You look at your lights, the lights pop on. How great would that be to have that kind of crazy, crazy power over your household?
We never get that lazy.
I just had one last question. It was about your idea for using the filtration method, because that's something similar that at the lab I'm working at we use for like gamma spectroscopy, and it allows you to get a really high resolution. And so I can kind of appreciate the elegance of the solution, the fact that it only took 6 days versus months. What triggered that for you to just kind of go that route?
Like I said, a nightmare. Really, it was a nightmare, and I thought to myself, correlation coefficient, correlation coefficient, 2 o'clock in the morning, and actually my fiance was there. What are you doing? I'm testing an idea. And I tested it, and actually, this is actually, I'll share with you guys, this is, further down. This is the first graphs of my work, and I found this, and it seemed promising to me, and so I went further and found this, and when I saw that, I couldn't believe it. I was like, perfect. Everybody else said, I've read on IEEE, I say everybody else, somebody else may have done something similar maybe, but there it's all SVM, small wavelet transforms, all of this craziness with really complex equations. This just makes me look, I'm sad. Like, I don't want to do that. That seems crazy. And it just really surprised me, and I was really happy with it. It worked. So
It's a good method.
thank you. Thank you.